Use any method to prove the statements in 26 through 29. For all integers m and n, if m plus n is even, then m and n are both even, or m and n are both odd. Now, since the name of this channel is contradictoriness, I'm going to prove this by contradiction. So we're going to assume the negation of this statement to be true. Now, this original statement is universally quantified on m and n, so we're going to existentially quantify m and n. So assume there exists integers m and n such that, and now we have to negate this propositional statement where we have an if-then statement form. For the negation of this implication, we say that m plus n is even, and now we have to negate the conclusion. Now the conclusion is an or statement, and so we have to use De Morgan's law, which means this or statement will become an and statement, and we have to negate each component individually. So m and n are both even has to be negated. So since we have to use De Morgan's law, we would say that m and n are not both even, and we have to negate this. M and n are both odd. So m and n are not both odd. So since m and n are not both even, and m and n are not both odd, this means that exactly one of these letters is even and the other one is odd. Since it doesn't matter which letter we choose for which property, we say, without loss of generality, say m is even and n is odd. When I say without loss of generality, what I'm trying to say is that we're assuming that m is even and n is odd specifically. However, this technically means that either m is even and n is odd, or m is odd and n is even. However, we just need to prove the specific case where m is even and n is odd, since the other proof will be exactly the same, but with the letters swapped. So I'm not going to prove the same thing twice, where the letters are just swapped. I'm just going to prove the thing once, and by saying without lots of generality, I'll only prove the instance where m is even and n is odd. So now we have m is even, n is odd, and m plus n is even. The goal is to arrive at a contradiction. We're almost there. Since m is even, then m equals 2x for some integer x, and that's by definition of even. By definition of odd, n equals 2y plus 1 for some integer y. Since m plus n is even, then that means m plus n equals 2z for some integer z. Next, what we're going to do is we're going to substitute m and n with 2x and 2y plus 1 respectively. So by substitution, 2x plus 2y plus 1 equals 2z. Now we're really close to the contradiction. It's not so in your face yet, but to make this more in your face, but to make the contradiction more prevalent, what we're going to do is we're going to emphasize that the right-hand side is an even integer, where the left-hand side is an odd integer, which will be a contradiction. We'll have odd equals even, which is not possible. Now, the right-hand side already looks even. That's good. The left-hand side, though, is not obviously odd. So let's rewrite the left-hand side. By simplifying, we can rewrite this as 2 times x plus y plus 1 equals 2z. Now, why would I rewrite this left-hand side like this? Well, because now we have the left-hand side as 2 times some integer plus 1, which is odd. Since integers are closed under addition, x plus y is equal to some integer k. So therefore, 2k plus 1 equals 2z, which means an odd integer equals an even integer. That is a contradiction. So now we can't ignore this contradiction. This contradiction is so in your face. There's no way an odd integer could equal an even integer. That's impossible. But now we have to backtrack and see, where did we go wrong in this logic? Well, all of this logic is perfectly valid. I made no mistakes here. And so the only mistake I could have made was the assumption itself. What we assumed was the negation of the original statement. So if the negation of the original statement is false, then that means the original statement is true. And that's what we wanted to show. Thanks everyone, and I'll see you in the next video.